Okay, guys, so somebody mentioned that they were having some trouble with tonight's homework, starting at about question 29. I'm going to skip around and do a couple of these. I do want to leave a few for you to try. So understand that I'm not answering all the questions, but I will post all the answers after I collect this homework. So 29 says something about vinegar has a strong odor. We don't care. First thing you have to do, though, is look at vinegar structure and you have to figure out which is the ionizable hydrogen or which one of those four hydrogens would be coming off. And so if we look at acetic acid, it has a structure of CH3COOH, and this final H is the one that can dissociate. And this is truly an equilibrium where we would form acetate ions, anions specifically, and hydrogen ions. This is how acetic acid would dissociate. But let's go back and look at the question. And it says, the odor of vinegar, blah, 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 is a weak acid. List in order of decreasing concentration all of the ionic and molecular species present in 1 molar aqueous solution of this acid. So, since it is a weak acid, that means that most of acetic acid is going to be found unionized. This will be my major species. So the highest concentration is going to be acetic acid that just sat there and did nothing. And its concentration now is going to be greater than acetate anions concentration would be equal to the hydrogen ion concentration. And both of those would be much smaller. In fact, only about 5% of acetic acid dissociates in water. Let's skip down to something else. And says, like 31, explain why the ionization constant for Ka for sulfuric acid is larger than the ionization constant for sulfurous acid. So now we're going to look at structure. And you should be able to draw these structures. If you can't, that's something else that I can review with you. This is the Lewis structure for sulfuric acid. And if we look at acid strength, we're looking at how strong is this bond. So I wanted to bring up the idea that we had in the PowerPoint, which talked about, let's see, where was it? I think we talked about it already. I'm scrolling through the slides as I talk to you, which is probably very poor. But on slide 42, we talk about the bonds. And so the way they label them is this is bond B, and this is bond E, or A. So in an acid, this is the bond we want to weaken to make it a strong acid. If we do that, it's because we have electronegative elements out here pulling electrons away from the sulfur, which makes this oxygen pull more strongly on those electrons, making this bond easier to break. So the more electronegative elements I have on this nonmetal makes this bond easier to break. And so that explains typically all acid strengths. Let's see. So here we have, what is the ionization constant for this weak acid? Here they give it to us. The conjugate acid, the weak base, this. And so here's the Kb. So something like 35 is really just understanding that Ka times Kb has to equal Kw. And they almost always give it to us at 25 degrees Celsius, which means we'd use 1.0 times 10 to the negative 14th. If it is at a temperature other than that, they have to give you what the Ka is, because you are not expected to know those values. I think you can handle it from there. So it says gastric juice in the digestive produced in the stomach causes hydrochloric acid. Milk of magnesia is a suspension of this. An aqueous solution is sometimes used to neutralize the stomach acid. Write a complete balanced equation. Okay, so your stomach makes HCl. You drink milk of magnesia, which is this. Write and balance this equation. So magnesium's going to be bounded to chloride. Magnesium's +2, chloride's -1, so it'd be MgCl2. And hydrogen will be bonded to OH, which will give me H2O. And so in almost all acid-base neutralizations, especially Arrhenius acids and Arrhenius bases, give us a salt and water. So I need 2 chlorine, so I need a 2 over here. And that gives me 4 hydrogens total, so I need a 2 here. I have 2 oxygens, so there it is, all balanced. Easy peasy lemon squeezy. So something like 39 is a little bit harder to figure out, but I think you can do it. You might want to consider looking at Ka values, and if you compare the Kas for each species, you should be able to figure out which one's stronger. So, and here if we have something like 37, this one is this one stronger or is this one stronger? And that goes back to the idea of what makes something a good acid or base, which was also talked about in your slides. And I think I talked specifically about bases. I'm looking to make sure I did. So, not seeing it. Okay, so for something to be a good base, we want to be able to stabilize that positive charge. And which conjugate acid? This is a stronger acid. Okay. I think I'll come back to that question another time. But I hope this helps you for now. We're running out of time. I'm almost at 8 minutes, and that's about the max I like to do. I'll make another video.